So in the last class, I introduced the Shannon-Fano-Elias coding technique. So recall that previously we've already seen an optimal coding scheme, which is Huffman coding. Right? So among all possible prefix-free codes, this is the one that achieves the minimum expected length. But we saw that there's a problem with extending Huffman codes to block encoding of symbols, in the sense that the computational complexity blows up exponentially in the size of the block. Right? And if we are to even attempt at getting close to the entropy rate, or even try to get close to the entropy of the source, then Huffman coding will not cut it. Right? So towards that, I introduced the Shannon-Fano-Elias code, which is not really optimal. It's much worse than Huffman coding. But as we'll see, an extension of the ideas of the Shannon-Fano-Elias code will give us a very efficient coding scheme. All right. So what did we do in the Shannon-Fano-Elias coding? For any symbol, you first compute the modified CDF, right, which is defined as follows. And then the encoding of any particular symbol is the first L of x bits in the binary representation of this modified CDF corresponding to the symbol x. All right. And how do you decode? Well, the decoding of x or decoding of .C1, C2 up to CL. So if you take the binary, if this is the base 2 representation of the code word, then this is equal to x if .C1, C2 and so on, CL lies between fx bar of x and fx bar of x minus 1. Right? So the geometric intuition for this is the following. Let's consider the CDF of the distribution that is given to us. So for each symbol, the midpoint of each of these intervals corresponds to the value of the modified CDF. So this would be f bar of 0, this is f bar of 1, this is f bar of 2, and so on. So each of these corresponds to some real number between 0 and 1. When you truncate the binary representation of this particular number, you will get some number which is less than that number. Right? So if I take the binary representation of f bar of 2 and then truncate it to some number of bits, then that will correspond to the binary representation of some number which is less than f bar of 2. So the more number of bits that I truncate from f bar of 2, the smaller that number is going to be. All right. So if I truncate too many bits, then potentially the truncation of that particular number may lie somewhere over here. That's what we want to avoid. We want to make sure that the truncation of f bar of 2 lies precisely in this particular interval, and it doesn't go outside the interval. Right? Because that's how our decoder operates. We've defined the decoder that if what I see is a real number within this particular interval, then I declare 2. If I see a number that is in this particular interval, I declare 1, and so on. So if I truncate too many bits, then potentially the number that I see could go outside this particular interval, and that will lead to a decoding error. But if I don't truncate too many bits, then obviously I can guarantee decodability. It's going to lie in this particular interval, but then the length of the code word would be long. So we want that balance between the length of the code word, and we also want to guarantee that the symbol can be decoded correctly. So what is the minimum number of bits that I need to truncate so that I ensure that that the truncation lies in the corresponding interval? That's the objective. Right? So that's the high level idea behind the Shannon-Fano-Elias coding scheme. And we've seen that the expected length is guaranteed to be, so it's obviously greater than or equal to h of x, because we've seen that any prefix-free coding scheme has an expected length greater than or equal to the entropy, but it's less than or equal to h of x plus 2 bits. So unlike the Huffman code, which is guaranteed to be within h of x and h of x plus 1 bits, the Shannon-Fano-Elias code is guaranteed to be between h of x and h of x plus 2 bits. All right? In fact, it's going to be even worse. It's going to be between h of x plus 1 and h of x plus 2 bits. Precisely because we've defined the lengths in this particular fashion. Right? So in expectation, the expectation of L of x is going to be greater than or equal to expectation of log 1 over p of x plus 1, which is h of x plus 1. But it's less than or equal to expectation of this plus 2. So it's the expected length is guaranteed to be less than or equal to h of x plus 2 bits. Okay, so this is fine, but clearly what I've defined is something that is suboptimal compared to Huffman codes. But now we'll see a method where we can generalize this particular approach even for block encoding. Right? And the main advantages of the Shannon-Fano-Elias code was that to encode x, we only need fx bar of x and px of x. Alright, so these are the only two things that I need in order to find the encoding of any particular symbol. I don't need to construct the rest of the code book. So let's see how we can generalize this to even larger alphabets, or more precisely to blocks of symbols. So let's say that I have some sequence x1, x2 up to xn that I wish to encode. Alright, so here we are assuming that each xi is coming from some alphabet 0, 1, 2, 3 up to m minus 1, where m is the size of the alphabet. Okay, we're going to assume that each xi is coming from this alphabet. If not, we map it to this particular alphabet. Now I can represent each such sequence, x bar, as a real number between 0 and 1. And I can do so by considering the emery representation of real numbers. Right, so I'll write this as 0.x1, x2, x3, and so on up to xn. And this corresponds to the real number, which is given by summation I equal to 1 to n xi m to the minus I. Right, so this number is guaranteed to be between 0 and 1. One of the main reasons why I want this representation is now that because of this, I have a particular ordering on sequences of length n. And the ordering on sequences of length n and length n plus 1, there's a natural ordering that comes up because of it. Right? For example, let's assume that m is equal to m is say 3. Alright, so each symbol, so I have a sequence say 0, 1, 1, 2, 2, 1, 1, 0, and I have 0, 1, 2, 1, 1, 0, 1, 2. And take another sequence, say 0, 1, 1, 2, 2, 1, 1, 0, 2, 1. Let's call this x1, x2, and x3. What can you say about the ordering between these two? Which one is greater than which? Let's take x1 and x2. Which one is x1 greater than x2 or x2 greater than x1? X2 is greater than x1. What about x1, x2, x3? Yeah? Let's take x3 and x1. X3 is greater than x1, right? But it's less than x2. In particular, let's say that I have two sequences, one of which is a prefix of another sequence. What can you say? Which would be larger, the prefix or the one which is a prefix? So if x1 is a prefix of x2, is a of x2, which one would be larger? x2 is larger than x1. Right? And in particular, this is less than, suppose x1 is something which is say 0.b1 x2. Say this has this x1 of 1 up to x1 of k. Maybe x1 is a k length sequence. Then this is going to be less than x3, which is equal to x1 of 1 up to x1 of k minus 1. The first k minus 1 symbols are the same, but the k plus 1th symbol is incremented by 1. Sorry? So the kth symbol is incremented by 1. Alright, to be more precise, this is less than x1 plus m to the minus k. Alright, this is a more precise version of what I'm trying to say. Alright, because you have to be a little careful depending on what the kth symbol is. Right, any questions so far? Alright. So now if we are to find the Shannon-Fano-Elias code for a sequence of n symbols, what should we do? We need to compute f xn bar which is summation over all possible an which are less than xn of this particular quantity, right? And one thing to note is that this statement is true, or this is true even if the symbols are not IID. For example, if I have some joint distribution on blocks of n symbols, but it's a stationary distribution, then the same Shannon-Fano-Elias coding still goes through. Just think about it a little. All right. So this is, I need to compute fxn and I need to know pxn. If the sequence is IID, then this is just a product of px of xi. But more generally, I can write this as xi given xi minus 1 this is equal to p x n minus 1 times p x n given x n minus 1 of x n given x1 through xn minus 1. For example, if this is a first order Markov chain, then pxn of xn is just pxn minus 1 of x1 through xn minus 1 times pxn given xn minus 1 of xn given xn minus 1. All right. If it's a kth order Markov chain, again, all of this just goes through. The main point is that you can break xn down into this sort of recursive formulation to compute the probability of a chunk of n symbols. It boils down to finding the probability of a chunk of n minus 1 symbols times something. In particular, finding pxn has complexity just order n. Right? I just need to do n multiplications. Okay. So the question is, can I do something similar to compute f bar of xn? Right? If I use the sort of naive approach of finding all possible sequences an less than xn and summing over all of these, what would be the complexity? How many terms do I have in this summation? Order. Like, does it grow linearly with n, quadratically with n, cubic with n? How many terms do I have in the summation? You have exponentially many terms, right? So if I use the brute force approach, then finding the summation requires exponential in n time. That is something that I want to avoid. All right. So the naive way of finding the Shannon-Elias code again has complexity that grows exponentially with n. However, there is a simpler way of computing this. Sorry, I should have. There's a slight error over here. This should be plus pxn of xn divided by, right? That is what f bar of xn is. So let me define this other quantity gxn of xn to be summation an less than xn of This should also be an, right? So this is gxn. If I'm able to compute gxn efficiently, then I can find f bar xn efficiently. Alright. So f bar of xn is gxn plus p of xn divided by 2. I'm sorry? Yeah. Which? Alright. Now it turns out that there's a simple recursive way of computing g of xn. And the basic idea is the following. So first let me write down the recursive formula. This is equal to, I need to express gxn in terms of gxn minus 1. Right? So this is equal to gxn minus 1 plus pxn minus 1 times summation a less than xn p xn given xn minus 1 of xn given xn minus 1. So if this is IID, then gxn, this is equal to gxn minus 1 plus just because this is simply pxn of a, right? So this quantity is just gx of xn. So I leave this as a homework for you to show. But basically the idea is to decompose this sum or break down this sum into multiple parts, right? And to do that you make use of this particular observation over here. You take a look at the prefixes, right? And this ordering essentially helps you, right? But I leave that as an exercise. So here is a sort of pictorial representation of what happens when you look at sequences of symbols. Right, so let's just for simplicity, let's assume that there are three symbols in my alphabet: 0, 1, and 2. Alright, there's some probability that x is equal to 0. And let me use a different color. So this is the CDF of let me just plot. So let me look at g of x. Say fx px is say 0.1, 0.3 and 0.6. Suppose this is my distribution. Alright. So three symbols with probabilities 0.1, 0.3 and 0.6. What is g of 0? Is equal to 0. Right? What is g of 1? Point 1. Right? So gx is 0, 0.1. What is g of 2? 0.4. Right? It's basically g of some particular symbol is the sum of all of the probabilities of all the symbols which are less than that particular symbol. Right? So g of 0 is just 0, g of 1 is 0.1, and g of 2 is 0.1 plus 0.3, which is 0.4. Let's plot these values. So g of 0 is 0, g of 1 is whatever 0.1, and g of 2 is 0.4. Let me keep it a little to scale. So this is 0.1. Let's say this is 0.4, and this over here is 1. It's not exactly to scale, but you get the picture. Right? So now what happens to, so this is for one symbol, right? Let's suppose now I have a sequence of two symbols now. So I have 0, 0, 0, 1, 0, 2. Zero, 1, 0, 2, and I have 1, 0, 1, 1, 1, 2. I have 2, 0, 2 1 and 2 2. Again, you have to think of these in the emery representation. So 0 would sort of be 0.0, 1 is 0.1 and 2 is 0.2. So when you get a new symbol, automatically the suffix of 0 is 0, of 1 is 1, so that becomes 0.10. So effectively 1 is the same as 0.1, which can be suffixed with any number of zeros. Right? So if you are looking at a sequence of length k, then you should think of this as 1 followed by k minus 1 zeros. Is that clear? Alright. So essentially you have to think of these as real numbers. Alright, in the emery format. In this case, the ternary base 3 notation. Okay, so what would be P of 0 1? What is G of 0 1? It's still 0. What is G of 0 0? How many sequences are below 0 0? Nothing, right? So that's 0. What about 0 1? Correct. So it's basically G of 0 1 is just P of 0 1, which is P of 0 times P of 1. Right? We're assuming that the sequence is IID. And what about G of 0 2? It's P of 0 1 plus P of 0 0, which, if you think about it, is just P of 0 times G of 2. Do you agree? That's correct. I'm sorry. That's right. Alright, so in general, for any alphabet, 0A is P of 0 times G of A. For an IID sequence. Alright. So this will look something like this. What is G x2 of 1 0? It's equal to exactly px of 1, right? Because it's px of 1 times summation over all a less than, or this would be P of 0 plus P of 1 plus P of 2, which is just, this should be Px of 0. So this quantity is P of 0, 0 plus P of 0, 1 plus P of 0, 2, right? Because these are the sequences which are less than 1, 0. Which is just P of 0. Alright? What about P of 1, 0? Sorry, P of 1, 1. It's going to be P of 1 plus P of 1 plus P of 1, 0. Right? So this is P of 0 plus P of 1, 0, which is G of 1 plus P of 1, 0. So you can go on calculating this for different values. And this would basically look something like this. Any questions? So if you notice, there's a pattern. Initially, I had these three intervals, right, corresponding to whatever. The Gx was essentially partitioning 0, 1, the interval from 0 to 1, into three subintervals. From this subinterval, and this subinterval. When I looked at Gx1, x2, this essentially partitioned each of these intervals into three subintervals. It partitioned this into three subintervals, and it partitioned this interval into three subintervals. All right, and the width of each subinterval is essentially P x1, x2. All right, so a sort of visual representation of this is the following. I start with the interval from 0 to 1. And then I partition this into three intervals corresponding to symbol 0, corresponding to symbol 1, and corresponding to symbol 2. Right? The width of this interval is the probability of 0. The width of this interval is probability of 1, and the width of this interval is probability of 2. When I look at pairs of symbols, I'm essentially partitioning each of these intervals into subintervals. Take a copy. I'm just partitioning each of these subintervals into each of these subintervals. Right, so this is 0, 0, 0, 1, 0, 2, 1, 0, 1, 1, 1, 2, and 2, 0, 2, 1, and 2, 2. Alright, and the width of each of these subintervals is the probability of occurrence of that particular sequence of symbols. Alright. Okay, so what does the Shannon-Fano-Elias code do in such a context? What it does is it finds, so you first, let's say I want to find the Shannon-Fano-Elias code for some particular sequence, right? Let's say 1, 2. You first find the midpoint of the interval corresponding to 1, 2. This is g of 1, 2 plus p of 1, 2 by 2. This is f bar of 1. Alright. And now you truncate f bar of 1, 2 to within a certain number of bits, while making sure that whatever you get is guaranteed to lie somewhere in this range over here. Okay, does that make sense? So this is some number. Hopefully, do you all agree that the midpoint of this particular interval will correspond to f bar of 1, 2? Do you see that? So, what is the width of this particular interval? P of 0, 0. What is the width of this interval? P of 0, 1, right? So, what is the value, or what is this particular number going to correspond to? It's equal to the lengths of each of these intervals. Do you agree? Which is exactly equal to P of 0, 0 plus P of 0, 1 plus P of 0, 2 plus P of 1, 0, 1, 1 and 1, 1, right? Which is exactly G of 1, 2, right? So the left end point of this particular interval is G of 1, 2. And the width of this interval is P of 1, 2. So the midpoint of this corresponds to G of 1, 2 plus P of 1, 2 by 2. Alright? So the midpoint is exactly F bar of 1, 2. So this gives you some particular number, right? Some number between 0 and 1. And then you truncate this. If you truncate it, you'll get some number which is less than F bar of 1, 2. Because you're truncating bits, right? And if you truncate just enough bits, then it's going to lie somewhere between F bar of 1, 2 and F bar of 1, 1. Does that make sense? Not too convinced? Okay. So, do you agree with the point that the midpoint of this interval is exactly going to be f bar of 1, 2? Right? Does everybody agree with this, or are there any questions about this? So, the midpoint of each of these intervals will be exactly g of that, f bar of that particular pair of symbols, right? And what do we want to ensure? What does the Shannon-Fano-Elias code do? It takes f bar and truncates it to a certain number of bits. What does the decoder do? It takes this sequence of bits, looks at the real number that corresponds to that, and if that real number lies between f bar of something and that plus 1, then it decodes. So how does the decoder work? What does it do? It outputs some sequence xn if basically the code word bits C1, C2 up to say I see a sequence of k code word bits. If this lies between f bar of xn minus m to the minus n and f bar of xn. So in this particular example, as long as the decoder sees a number between f bar of 1, 1 and f bar of 1, 2, it decodes it to be 1, 2. If it sees a number between f bar of 1, 2 and f bar of 2, 0, then it decodes it to 2, 0. If it sees a number between f bar of 2, 0 and f bar of 2, 1, then it outputs 2, 1, and so on. Alright? And so if we want to ensure that the decoder operates correctly, if what is decoded is exactly equal to the source, then we have to make sure that this sequence lies exactly in this interval between f bar of 1, 1 and f bar of 1, 2. Right? So you agree with this statement? Because I've specified the decoder. This is exactly what the decoder is going to do. So by truncating bits, you're sort of reducing the number, right? And you want the truncation to lie exactly in this particular interval between f bar of xn minus 1 and f bar of xn. Right? So that fixes how many bits you can truncate. And the Shannon-Fano-Elias code says that if you truncate up to ceil of log 1 over p of xn plus 1 bits, this is guaranteed. Alright, but in principle, if we want the decoding to be correct, we just truncate enough bits so that you truncate the minimum number of bits so that it lies precisely in this particular interval. Right? Yeah. Can you speak up? So my claim is that the left, are you talking about the decoding interval or the? So the decoding interval is this, right? I'm taking the decoding interval to be between f bar of 1 1 and f bar of 1 2. Why am I taking this to be the interval? Because if I take the encoding of 1 1, right, I know that it is going to lie to the left of f bar of 1 1. It's never going to lie to the right because I'm truncating the code word corresponding, the number corresponding to f bar of 1 1. So that's precisely why I can take it to be between. The previous symbol before that, that's all. Right? That's what this is exactly. Question?
The value f bar of xn minus m bar minus n.
Yes.
It is being included in both this symbol and also the previous symbol. So doesn't that create some ambiguity?
Okay. So maybe I should be a little more precise. It should be, you're right. Let's say I keep it between in this particular interval. I need to exclude one of the ends of the interval. Let's say I just exclude the right end of the interval. The Shannon-Fano-Elias code is more conservative in this particular way, but in principle, as long as I have a nice enough partition and I ensure that the code word lies within this non-overlapping intervals, I'm good. Okay. So let's try to use this idea to go sort of one step further, to look at it in a slightly different way. All right. Let me take this partition. Alright, so this is so I'm taking pairs of symbols and I'm using the probabilities to partition the interval from 0 to 1 into subintervals. The width of each subinterval is equal to the probability of that sequence occurring. Alright. Now I'll take another copy of the interval from 0 to 1 and I'll successively partition this into subintervals of equal length. Alright. So first I look at the partition, which will be labeled 0 1. Alright. 0 0 0 1 1 0 1. So I'm looking at binary partitioning. You can think of this operation, right, obtaining this particular partition as an Emery partition. But this Emery partition is not a uniform Emery partition. the partition is based on the probabilities of the sequences. Okay. Now let me look at a binary partitioning of the interval from 0 to 1, but I'll look at the uniform binary partitioning. So I have 0, 0, 0, 1, 1, 0, 1, 1, and then I subpartition this into 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, 1, 0, 0, 1, 0, 1, 1, 1, 0, 1, 1, 1. Okay, so these are two different ways of partitioning 0 to 1. So one is in emery based on the probabilities. The other is in binary, uniform partition. What I'm trying to get at is trying to design a mapping between intervals over here and intervals over here, so that each interval over here would essentially correspond to some subinterval over here, okay, in some particular way. So to think about that, let's look at the encoding of one particular symbol. Let's say the symbol, again, maybe it's best to take the symbol 1, 2. My goal is to find the encoding of 1, 2 in this pictorial fashion. It's not a bijective mapping. It's some mapping. I'm sorry? So I'll try to come to that. All right. What I want is, we'll see. When I'm saying mapping, it's in a slightly loose sense. All right. What I want to do is, for each symbol. So let's look at this subinterval over here, or maybe let me describe it in a different way. So suppose that we want to encode some number x1, x2. All right. So the associated the interval associated with x1, x2 is going to be the interval g x1, x2. Let me use and g remember that fx1, x2, which is the CDF, is equal to gx1, x2 plus px1, x2. All right. So this is the interval that is associated with gx1, x2. The left end of the interval is g of 1, 2, and the right end of the interval is f1, 2, which is also equal to g 2, 0. that's f bar. The midpoint is f bar. All right. So the left end is G, the right end is the CDF, and f bar is basically the midpoint between these two. All right. So corresponding to each sequence of symbols, I have an associated interval. All right. The encoding process that I will consider, which is not exactly the Shannon-Fano-Elias encoding, but something slightly different, is the following. So consider, so you keep partitioning So you take the interval from 0 to 1 and you keep partitioning this into subintervals. Alright, you partition this uniformly. So remember, initially we started with 0 to 1, which was one interval. Then I partitioned it into two intervals from 0 to half and half to 1. And then I sub-partition it into 0 to 1/4, 1/4 to half, half to 3/4 and 3/4 to 1. And then again sub-partition. I keep doing this process until a certain point until there is one subinterval that is contained in this particular interval. So how many times I would have to partition depends on the values of the probabilities. All right, just so you'll take the code word to be the binary sequence that corresponds to this particular interval that you get. Let's start with a very simple example. Say I have only one symbol to encode, and let's take the same probabilities 0.1, 0.3 and 0.6. I start with the interval from 0 to 1. Let me partition this into 0 to 0.1. This is half. 0.4 and the rest. So this corresponds to the symbol 0, the source symbol 0. This corresponds to the source symbol 1, and this interval corresponds to the source symbol 2. Now let's let's try to find the encoding of each of these symbols, starting from 2, because that's the highest probability symbol. Alright, so first let's partition 0 to 1. The first step is you partition it into 2 intervals. Alright, half and 1. The left interval is labeled 0, the right interval is labeled 1. Now you check if one of these intervals lies within this particular interval. Does it? Yes, right? So we see that this interval is a subinterval of this particular interval. So you stop and declare the code word corresponding to 2 to be equal to just the bit 1. Now let's try to do the same for the other symbols. Let's try for 1. So the first step is you partition the interval into 2. The first interval is 0 to half, which is going to be labeled 0, and the second interval is from half to 1. Now neither of these intervals lies within this particular subinterval. Right? So let me further partition this into 2 more subintervals, from 0 to 0.25 and so on. Does one of these subintervals lie within this particular interval? It doesn't, right? So let's again partition this into more subintervals. What about now? Right, so let's see the labeling of each of these intervals. These intervals would be labeled 0, 0, 0, 1. Sorry, there should be 3 bits: 0, 0, 0, 0, 0, 1, 0, 1, 0, 0, 1, 1, and so on. So we see that this interval lies completely within this particular interval. So you declare this to be the code word corresponding to 0, 1, 0 to be the code word for 1. Oh, is it? Okay. Yeah, I guess it was not to scale. So that's okay. If there are 2 subintervals, then you declare one of them. Right? Let me see, I think. Right, I think this should have been somewhere over here, right? So I can choose any one of these. Let's say I choose this to be the interval. Whatever I do it in any systematic fashion. This is equal to 0, 1, 0, say. Alright. Now let's try to do the same for the symbol 0. We want to encode the symbol 0. and you keep partitioning the interval into sub-intervals such that that sub-interval lies strictly within this interval. How many times would I need to partition? All right. So I basically need to do this 4 times, and the encoding of 0 could be taken to be 0, 0, 0, 0. Question? Which one? What do you mean? Not so. You'll see it's not so bad. All right. This is sort of. I'm not. This is a visual representation, but there's a more efficient way of doing this, because it's not too difficult to calculate the endpoints of these intervals efficiently, right? Because they're all binary sequences, right? So, okay, so this is encoding, and what does the decoder do? Well, the decoder, all it has to do is it's given a particular sequence, right? Either 010 or 001. It looks at the interval. It first constructs the interval corresponding to this. If both the left and the right ends of this interval are strictly within one of these subintervals, it declares that symbol as the output. All right? And that's it. Is the encoding and decoding process clear? Right? In a sense, this is... Question? So in a sense, this is very similar to what is already being done by the Shannon-Fano-Elias code, if you think about it. Except that how do you identify the endpoints of the interval is a little bit different. The Shannon-Fano-Elias code always considered the midpoint, or basically f bar, as one of those as the subintervals, whereas here the subintervals are identified by G and F. Right? So this is a process known as arithmetic coding. What I've given is a pictorial or a graphical representation of the encoding and decoding, but the implementation can be done in a very efficient manner.
Like once we have encoded, we don't need to do intervals.
I'm sorry?
Once we have encoded,
Yes.
we don't need the intervals to decode.
You don't need the intervals to decode.
Because you can just do this now.
You can, exactly. So, what do you mean? You can give the map?
Like this encoded to this.
So you don't need to construct the code book. Is that what you're saying?
Since like we can decode based on these. It's like we don't need to find check if this interval is.
You don't, yes. Essentially, you just take maybe the left endpoint of the interval. So the left endpoint of each of these intervals is just the binary representation of these numbers, right? So all you need to verify is does this point lie in this interval or this interval or this interval? That's all. So decoding is actually very efficient. This is just a comparison. You need to think about how do you find out how many bits or how many steps to go through to make sure that this subinterval lies completely within this particular subinterval. And that can also be done in a very efficient manner. This is sort of a recursive approach, but again can be done very efficiently. Right? Now it turns out that the expected length of the arithmetic coding is again going to be less than or equal to the entropy plus 2 bits. So it's going to be no worse than the guarantees that you have for the Shannon-Fano-Elias code. And as for the Shannon-Fano-Elias code, this can also be, you can also use this for non-identically distributed sources. In fact, non-independent and identically distributed sources. All right. So I'll give some more resources for arithmetic coding in the lecture notes, but we won't go into too much detail about this. So so far we've seen two good coding schemes. One is the Huffman code, the other is the Shannon-Fano-Elias or the arithmetic coding scheme. It turns out that arithmetic coding is more efficient, but this is a minor issue with, say, Shannon-Fano-Elias or the way I've described arithmetic coding. So let's again go back to the Shannon-Fano-Elias coding scheme. Effectively, if I want to encode something, I just need to compute g of x and p of x. Right? And I can do this for any sequence. What is the complexity of computing this? How does the complexity grow with n? If I just have to compute g of xn, how many steps do I need? Linear, right? Because I can express g of xn in terms of g of xn minus 1. I can express g of xn minus 1 in terms of xn minus 2 and so on. So just a linear number of steps is enough to compute g of xn. Right? So this complexity is just linear in n. This for pxn, again the complexity is linear in n. So overall the complexity is still just linear in n. Alright? So the number of operations is just linear in n. And then I need to truncate, which is again not too hard. So it seems like I have an extremely efficient encoding mechanism, right? But there's a catch. Suppose that n is very large, right? What practical issues can you potentially run into? Precision issues, precisely, right? Because if n is large, then you need to be able to compute gxn to very high precision. And the precision that is required grows exponentially with n. So that becomes the bottleneck, right? And that's precisely why you can't directly use the Shannon-Fano-Elias code. But as it turns out, the arithmetic code allows, or an adaptation of the arithmetic code allows you to do that more efficiently. The reason being that if you look at, let's go here, the subinterval corresponding to each of these. So if you look at the interval 0, 2, right, the subinterval corresponding to 0, 2, this is a subinterval of the interval corresponding to the symbol 0. So it turns out you can bypass this precision problem by, in intermediate steps, you rescale the interval so that it again lies between 0 to 1. So effectively what you do is, again I'm being very loose over here, it's a little more involved, but basically after every time you encode maybe a couple of symbols, you rescale the interval and bring it back to 0, 1, and then output the first few bits of the encoding. Alright, and then basically now you rescale to 0, 1, and then you proceed as you did earlier. It's very interesting, but maybe it will take time, so I won't cover this in class. But it will give you some resources where you can find out more about this. Right. Any questions? Okay, so let's stop here.